Now we're going to be solving some exponential equations. Remember, we have solved exponential equations before, but we only could solve certain ones. Ones where I could rewrite both sides of the equation with the same base. Now that is no longer necessary with the power of logarithms. So now, uh, notice that I've got an exponential equation. 10 to the x equals 1722 here. So what I'm going to do is apply a log to both sides. Now I am writing this log without an explicit base, which means that I'm using the common logarithm of base 10. Now based on my logarithm properties sheet, which I have here somewhere, if the base of the logarithm and the base of the exponential part match, then log base b of b to the x is just x. So what I have here is log base 10. If I want to emphasize it, I can write in that 10. Log base 10 of 10 to the x, well, that is just x. So x is equal to log of 1722. Now that is my exact answer. I can get a decimal approximation. Oh, and notice my instructions did say to round to the nearest thousandth when necessary. So I can bring out my calculator, and I've got a log button on this calculator. Log of 1722. And that will give me approximately 3.236. So x is approximately equal to 3.236. The wavy equal signs means that it's approximately equal. This log is well, it's not even exactly equal to this. If I wrote down every digit I see, that's still a decimal approximation. Oftentimes people will just not bother with the wavy equal signs, but that is how we indicate that it is an approximation. All right, so that was number one. Let's move the calculator out of the way and do number two. So now, notice on this one, I used that property where if the base of the logarithm matches the base of the exponential part, then they can cancel. So I don't want to take log base 10 of this because I won't have that nice canceling property. I'd rather take the natural log. So I've got the natural log of e to the 3t is equal to the natural log of 152.9. And remember, ln is really just another notation for log base e. So log base e of e to the 3t is equal to 3t by that same property, property C on our properties list. So now, again, I want to get my calculator out for this decimal approximation. The natural log of 152.9 is 5.029. Let's see, so 3t is approximately equal to, I'm actually going to write down more decimal places than were called for. I'm still going to round my answer to the correct value, to the thousandth, like I was asked for. Now notice that this is what 3t is equal to. So then I'm going to divide this by 3. And t is approximately equal 2. So I want to round to the nearest thousandth, and that will give me 1.677. So there is number 2. Now let's look at number 3. Notice with number 1 and 2, if I take the log base 10 or a log base e, a common log or a natural log, I have buttons on my calculators for those two. If I tried to take log base 3 of both sides, well, technically I can take log base 3 of both sides, but it's not going to be very helpful with my calculator. So what I'm going to do instead is use a completely different property. I'm going to take a natural log of both sides. So I take the natural log of both sides, and now I'm going to use a different property off of my properties list. I'm going to use property G, which is the one that says that if I have something where the entire input is raised to an exponent, I can pull the exponent out front to become multiplication. So this becomes x times the natural log of 3. And that's equal to the natural log of 91. So now I want to point out the natural log of 3 is just a number. It's not as nice a number as like 8, but it is still just a number. And I have x times a number equals another number, which means that x is equal to the natural log of 91 over the natural log of 3. I just divided both sides of my equation by natural log of 3, and I can do that because it's just a number. Now, I'm going to use my calculator to get a decimal approximation. So I've got the natural log of 91 divided by the natural log of 3. And when I put that in, I get 4.10, well, it will round to 4.106. So x is approximately equal to 4.106. Now, very often, when I teach this in person, people will say, well, why did you take the natural log as opposed to the common log? And you can do the same exact thing with the common log. Notice that if you type into your calculator the common log of 91 divided by the common log of 3, you get the exact same answer. You get 4.106. And actually notice that it's exactly the same as far down as it chooses to show us the approximation for. It does not matter which log you take. Your calculator has these two buttons. You can use either one. The only thing you can't do is take a common log of one side and a natural log of the other. You have to take the log of the same base for both sides, but other than that, you can use either one. And you need to be comfortable using either one. But they will both work and give you the same answer. All right, so finally, let's do number 4. Now, last time we took the natural log on both sides, although we saw how it was the same for the common log. This time, I'm going to write in taking the common log of both sides. So the common log of 5 to the 2m minus 7 equals the common log of 72. I can pull the exponent out front. Notice that now my exponent is a little more complicated than it has been. When I pull it out front, I need to write parentheses around it. That'll be 2m minus 7 in parentheses times log of 5 equals log of 72. I'm going to divide the log of 5, or I'm going to divide both sides of this equation by log of 5, so I get log of 72 over log of 5. And then there's actually several different orders you could put this in, but we can go ahead and get a decimal approximation for that number. This is just a number divided by another number, so the whole thing is just a number. So the log of 72 divided by the log of 5. And again, maybe if I want to hold this so that the light will make the calculator screen visible. Again, you get the exact same thing if you use a natural log versus a common log. So I have 2m minus 7 is approximately equal to 2.65724. Since I'm not completely done, I'm going to write a few more decimal places than I need to. Then I'm going to add a 7 to both sides, and I can do that straight in the calculator. So 2m is approximately equal to 9.65724. And I'm running out of room on my sheet here. Well, I just write on the brown page. And I need to divide by 2. And so I get m is approximately equal to 4.829. And there is my final answer. That is what m is approximately equal to. Now finally we have one more problem to work. Make sure that shows. Alright, so I have e to the x squared equals 789. Now here I could take the common log and use that property g like we have been. Or I can take the natural log and use the fact that the natural log has a base of e, which I think is the nicer way to work this particular problem. So I'm going to take the natural log of both sides of this equation. Then the natural log of e to the x squared is just x squared equals the natural log of 789. And now I'm going to remember that this is just a number. One thing that we can do is just wait until the very end to punch any of this into the calculator. I had been bringing out the calculator as we go, but I've got x squared equals a number, which means that x is equal to plus or minus the square root of that number, and that number is the natural log of 789. So I can break out the calculator one more time and type in the square root of the natural log of 789. So x, now it's an approximation, is approximately equal to plus or minus 2.583. And so there we have our decimal approximation. One thing that when people are faced with this may concern them, since we have been working problems where negatives weren't allowed, and in fact we did use a logarithm. But notice we took the logarithm of both sides when everything was positive, which is okay. And it is okay to have negatives in an exponent. Now, As a matter of fact, this one is going to be squared, so that would become positive anyway. But exponential functions can have negatives or 0 in them. The domain of an exponential function is the set of all real numbers. It's the domain of a logarithmic function that's the set of all positive numbers, and you have to be careful about not putting 0 and not putting negatives into a logarithm. But solutions, as far as this one are concerned, can be any real number, and I have two very good solutions right there. And that is it for solving exponential equations.